Good evening. Here are yet again with another lovely session of CENG 3325 Structural Analysis. This is the 21st video in the lecture series, and today, or this evening, we're going to be looking at an example of applying the method of virtual work to a simple frame. So this is just going to be one big example working through an entire problem of finding virtual work, or using virtual work to find the displacement of a joint in a frame. So consider the following system. So we are going to look at a two-frame member, and obviously the more complex the system you had, the more time-consuming and involved it would be mathematically, and etc., etc. So we're going to have a system like this. It's going to have a rigid joint up at the top left. There will be a pin joint down at the bottom corner here, the bottom left corner, and there will be a roller joint here. There'll be a roller joint here. And I have made this I have optimized this for time, although it's still going to be a fairly lengthy process to go through the entire series of steps. So we have joints A, B, and C here, and then we're going to have loads here, and these are going to be real loads of, let's see, along the column here, we're going to have a load of 1 kip per foot all the way up. Or maybe I'll draw the line first. So 1 kip per foot all the way to the top. And we'll have that going to the right. And then 2 kips per foot. Let me label that 1 kip per foot. And let's get 2 kips per foot along the horizontal here, along this beam. So this could be any number of things. Maybe this is like I don't know, maybe this is under wind loading and it's producing some downward load, some sideward load against the column here, and then there's some vertical load from self-weight and live load or something like that. But of course, this is purely theoretical. This could be any number of systems could produce, any number of loadings could produce this type of load. So we have joints A, B, and C, and the height of it, we'll need the dimensions. The height of this column is 15 feet, and the length of this beam is going to be 20 feet. So we have that, and then I'm also going to give us the material properties, or the section properties, material and section properties. Like most of these examples, I'm just going to stick with a nice friendly 29,000 KSI modulus of elasticity, aka my favorite material, good strong American steel. And I, the moment of inertia, is going to be 4,000 inches to the 4th power. It's good, strong American steel. Good stuff. Anyway, so all of this is given, and we want to find the rotation at joint B. We want to find how much this joint is going to rotate, and that measure is going to be in radians, how much this joint is going to rotate under the applied loadings. So considering the modulus elasticity, the stiffness of the material, the size of the cross sections, that sort of thing, how much is this going to rotate? Now, I am saying that both the column and the beam have the same cross section. In any real structure, that's very unrealistic. You're typically not going to use the same cross-section for your beams and your columns. That would be very unusual, very unorthodox to say the least, and not very efficient, but that does make our calculations a little bit simpler. But of course, realistically, you probably have we probably have more of a compact shape for your column and a beam that's more optimized for bending, but let's not worry about such things for now. So we have this is the kind of system that we're going to be working through. And this is this is what the whole video is going to go over. So the first thing we're going to do is I'm going to split this video into a series of large steps. The first step is going to be step 1, or step I, analyze the real system. Just like when we looked at virtual work for trusses and for beams, we have a real system and we have a virtual system. So analyze the real system. So the first thing I'm going to do, and step 1 underneath this, is going to be to get the external reactions. So, well, basically when I say analyze the real system, ultimately the end goal that I'm trying to get is to get the moment as a function of x for both the beam and the column in the real and the virtual system. Now, I can do this any number of ways. This is a nice statically determinate frame, so again, I can do this in any number of ways, but I could do this. I mean, I could go and do this, draw an exploded view right off the bat and solve for the internal reactions or the internal joint forces, that sort of thing. But in this case, I think it's going to make a little more sense to start with the external reactions. Just looking at this frame, this sort of speaks to me as saying, let's get the external reactions first. And typically when I do that, I like to do that, especially when there are, when the whole, oh man, I can't spell the word first today. Trying to write and talk at the same time. This frame here, it is going to have only 3 external reactions. So there is a vertical and a horizontal force at A and a vertical force at C. And so this thing as a single rigid body is statically determinate. There are other frames that are not statically determined as a rigid body, and you have to break them up before you can find even the member end reactions or the support reactions. So, but for something like this, it's very easy just to get the external reactions first before we start looking at the joint reactions. So I have this, I'm going to draw this out, have my dimensions 15 feet and 20 feet, and 20 feet, then I apply my loads. I'm going to initially just assume everything is to the right and upward, AX, AY, and CY. Then I'm going to have a distributed load up top of 2 kips per foot, and a horizontal load of 1 kip per foot on the column. And here again, we're just in statics, so really nothing that's groundbreaking here. So if you do a sum of moments about A, if you do a sum of moments about joint A, with again joint labels A, B, and C, if you do a sum of moments about joint A counterclockwise positive, you will have negative 15 feet times 1 kip per foot. Again, this is the moment caused by our horizontal load here, times its equivalent point load location or the distance to its centroid of 7.5 feet, minus 20 feet times 2 kips per foot times 10 feet. Times 10 feet. And then we'll add plus CY times 20 feet equals 0. And if you go and solve that, this is the moment caused by our distributed load here. And if you go and solve that for CY, you will get that CY is equal to 25.625 kips in the vertical direction, upward. All right, and for my next moment, I think I'm going to draw a little bit of extension here and define my own point. I'm going to define point D here, and point D is where the line of action of AX and CY meet. So that'll allow me to cancel out the moments produced by my by CY and AX. So I'm going to do a sum of moments about D here, this point that I've defined, and that will be negative AY times 20 feet minus 1 kip per foot. This is the moment by, again, the horizontal load on the column, times 15 feet times 7.5 feet. Then plus 20 feet times 2 kips per foot times 10 feet is equal to 0. And if we solve this, we'll get that AY is equal to 14.375 kips upward. And and this does make sense, because if we looked at this from the point of view of sum of forces in the vertical direction, this plus this would come to 40, which is exactly what 2 times 20 is. So that makes sense from the point of view of summing forces in the vertical direction. Then to get the AX, that's fairly straightforward. Sum of forces in the X direction. We will have, going to the right, 15 feet times 1 kip per foot, the horizontal load, the horizontal distributed load on the column, plus ax is equal to 0, and therefore ax is equal to negative 15 kips. And we now have the reaction on joint A, or the reactions on joint A, and all of the reactions on this joint, on joint C as well. Okay, so next I want to draw an exploded view of this structure and get a feel for the internal loads that'll be revealed. So I'm going to draw the exploded view of the structure and look at all of the internal loads and then solve for them using equilibrium. So draw exploded view. So I'm going to have column AB here and column BC, or sorry, beam BC. This is 20 feet long and this is 15 feet long. And then the reactions here. I'm just going to go ahead and put them in the directions that I know they are now. So I have my reaction AX, which is 15 kips, I have a vertical reaction AY, which is, oh, I managed to erase my column there, that's not good. Don't want any columns vanishing on us. AY then is going to be 14.375 kips. CY then, and CY is going to be 25.625 kips. 25.625 kips. Then my external loads in the horizontal direction, I'm going to have on my column a horizontal load of 1 kip per foot. And downward at 2 kips per foot. Downward at 2 kips per foot. Then in terms of our, now this joint here, let me just go ahead and label the, let me go ahead and give us some joint labels. We have A, B, B, and C, and then the internal forces that are revealed when I separate this, this is a fixed support, or a fixed joint I should say, so it's going to have a horizontal force, a vertical force, and a moment. So I'm going to say it has Bx here, and of course just like we did earlier in the semester, when we draw a internal force, we need to draw its equal and opposite force on the other piece. So maybe I'll give myself a little room, say that's Bx, and this is Bx. Then I'm going to assume, I just went ahead and assumed this one was up, although seeing this I know that's not really possible. So I'd have a By there, and an opposite By here. Then maybe a clockwise moment here, or a counterclockwise positive moment here. I would call that MB, and MB here. So I have a horizontal force, a vertical force, and a moment transferring through the beam. So I want to go ahead and get the internal joint reactions. That would be my third step. And maybe I'll just include it on the slides for reference. So 3 would be to get internal joint reactions. And I think I can actually just use the free body diagram of column AB for all of this. So you could use the beam as well, but I think I'll just use column AB. I used column AB in this case. Use the free body diagram of column AB. So if I do a sum of forces on this column, I will have negative 15 kips plus 1 kip per foot times the length of 15 feet, plus Bx is equal to 0, and so that's negative 15, that's positive 15, So that cancels out, and I'm left with bx is equal to 0. So there is no horizontal force being transferred through that joint. Then I can do a sum of forces in the y direction, again on the column. So let's say I have by. Again, for some reason, I just went ahead and assumed everything on this one was positive, but we know we're probably going to get a negative here. So by plus 15 kips is equal to 0, and by then is equal to negative 15 kips. By is equal to negative 15 kips. Then if I do a sum of moments let's go ahead and do sum of moments about B. A sum of moments about B. If I do that, sum of moments about B, I will have moments. Well, first I'll have MB. MB plus 15 feet times 1 kip per foot. This is the moment generated by our horizontal load here. 15 feet times 1 kip per foot times 7.5 feet minus 15 kips times 15 feet. And this comes to 0, of course. And solving for MB, you will find that MB is equal to 112.5 kip feet. 112.5 kip feet. So we now have our internal joint reactions. We have our internal joint forces, that are the forces that are being transmitted through joint B. We know there is no horizontal force. We know there is a force B that is actually opposite the direction of the arrows that we assumed, and we know that there is a moment of 112.5 kip feet in the directions that we assumed. So next, our final step on while analyzing the real system, step 4, we will obtain the real moment functions. Obtain real moment functions. So we'll obtain the real moment functions. So I'm going to analyze column AB and column BC, and I think for this I'll just use the method of sections in order to find m as a function of x across each column and beam. So let's consider column AB. We know from statics, mechanics, materials, and other things hopefully that once you have the end forces in a member, finding the internal forces is really easy. It's really just a method of sections at that point. The hard part is getting the end forces. Once you have those, the internal forces are relatively simple to solve for. Usually the hard part is the member end forces. So let's draw a isolated free body diagram. And what I'm going to do is I'm going to cut each of these as a certain distance x. I'm going to cut this at a certain distance x. And okay, so here's the thing. As we mentioned previously in when we were describing the theory of method of virtual work applied to frames, we can choose whatever sign convention we want. We can choose whatever end as the 0 point and whatever positive direction whatever direction as x equals positive. You can do whatever you want. The key thing is that you have to be consistent. So if I am, because again, we're going to do this twice, once for the real system and once for the virtual system. So on this member here, I could define this as the positive end, and maybe I could define this as 0 and upward is positive for my x, or I could define this end as 0 and this and downward is positive. I can do either one. But what I can't do is, for example, on the real system, show x as 0 here and positive up, and then maybe on the virtual system show x equals 0 here and positive down. That would be an inconsistent sign convention. It is imperative that you use compatible or identical sign conventions. So your 0 points have to be the same, or in other words, your origins have to be the same, and the direction of your positive has to be the same. If you don't do that, you'll screw this up. And maybe you'll kill somebody, so who knows. Alright, so column AB. I'm going to cut this at some point x. And I'm going to go ahead and define the 0 point as joint A at the base of the column. So we're cutting this at some point x, and so this doesn't have a length of 15 feet anymore, but it has a length of x. And then let's show the loads on this. So this is our origin point. I'm going to say that's x equals 0 there. And then I'm going to show the reactions and the external forces. So I have this horizontal load of my 1 kip per foot here. Of 1 kip per foot. And then I have reactions 15 kips. And an upward reaction of 14.375 kips. And an upward reaction of 14.375 kips. Then I'm going to show the shear and moment as, I'm going to assume them positive according to our initial directions. And for, I guess, completion, I should show the vertical reaction coming down on this. 14.375. Now, that is an internal force that is revealed by cut. However, because there are no vertical loads on the column or no axial loads on the column besides the joint force and the support, I know that no matter where I cut that, the vertical force is still going to be 14.375 kips. What will change is the shear and the moment. So I have some v as a function of x and m as a function of x. And I'm, again, on this, I'm going to go ahead and use our standard, just our standard structural engineering, sign convention for what positive shear and moment look like. So as long as if this is the 0 end and x is upward positive, a positive moment would be one that causes it to bend in this kind of shape here, like a smiley face, or to the right, if you want to think of it that way. So let's go ahead and work through that balance of moment. I'm going to go ahead and take moments about x. That way we don't actually have to solve for v as a function of x. You can if you want, but ultimately my goal is not to absolutely solve for every single shear and moment function in this frame. All I really need is the moment function, so why even bother getting v of x? I mean, I could, but this example is long enough as is. So let's do a sum of moments about point x. And first I'm going to have moment as a function of x, that right there, that couple. Plus 1 kip per foot. I'm going to get the moment caused by the distributed load. It's going to be positive. 1 kip per foot times x. That's the equivalent point load, and its moment arm is x over 2. And then minus this reaction here, the moment caused by that, minus 15 kips times x. Minus 15 kips times x. And we can and of course this equals 0 because this is in static equilibrium. And then m as a function of x for our column is going to be 15x minus x squared over 2. And of course our vertical forces here do not contribute to the moment because their line of action passes through point x. So 15x minus x squared over 2, and if I really wanted to, if I wanted to use like a consistent naming convention, I could perhaps call this MAB as a function of x. That would be the real moment on member AB as a function of x. We could even use that if we wanted to. And I'm not going to necessarily keep up with that naming convention for this particular example because there's only 2 members. But if you had a large frame with many different members, you would definitely want to use some sort of naming convention, organized naming convention, in order to keep track of everything. Next, I want to consider beam BC. I want to consider beam BC. So let's look at beam BC. And let's consider both the end forces and the moments. And the forces, let's just draw everything out. And again, I'm going to cut this at a certain distance x. So this is no longer a length 20 feet, this is of length x. So let's look at what forces are on this thing. We have our joint forces on joint B of upward 14.375 kips. Again, remember, I got a negative when we looked at the joint reaction, so we initially assumed it was downward on this member. We had to reverse that because it was actually negative, so now it's shown in its proper orientation. And a moment being distributed into this of 112.5 kip feet. 112.5 kip feet. Then we're going to have a distributed load across the top of this of 2 kips per foot. 2 kips per foot. And then we have a downward shear, V of x, again I'm assuming positive shear, and positive moment, M of x. And I'm not actually showing any axial force on this because there's not any axial force on it. If you look, there's no axial force on this end, which means there cannot be any axial force on this end. Again, I could go and actually solve for the shear, but I don't care about that, so I'm going to ignore it. So let's just go ahead and do a sum of moments about point x here. Again, here I'm using, this is my 0, and to x to the right is positive. Sum of moments about x, counterclockwise positive. This will be negative 112.5 kip feet. Then minus 14.375 times x. That is the moment about point x caused by the reaction here, 14.375 times x. Then plus 2 kips per foot. The moment, I'm going to get the moment caused by the distributed load, times length x, that is the equivalent point load of that, times moment arm length of x over 2. And then finally, plus the actual moment on the right end, the m of x that we're solving for. All this equals 0. And then solving for m of x, we get that solving for m of x and simplifying, I could go ahead and call this mbc, the real moment on member BC as a function of x is equal to 112.5 plus 14.375x 0.375x minus x squared. So we have now our two real moment functions. We have the moment function on AB and the moment function on BC. So we have now finished our first main step, and which is to fully analyze the real system. Next, we're going to move on to analyzing the virtual system. So step II, or Roman numeral 2, analyze the virtual system. Let us analyze the virtual system. So, as you recall from our previous work, when we do the method of virtual work, we apply a unit deformation to the structure, or a unit load to the structure that will produce a real deformation. So the whole idea is that virtual internal work is equal to virtual external work, and so we're going to apply a unit load to the structure. Now, in the previous examples, I've been looking for displacement, so we apply a unit force, like a 1 kip force, left, right, up or down, etc. But in this particular problem, I'm mixing it up a bit and asking us to find rotation. So here we're not going to be applying a unit force, rather we're going to be applying a unit couple to the structure. So let us consider this with our virtual system. Let's consider our virtual system. And our lengths are the same, our geometries are the same, but what's different is that all of our real loads now disappear. So we're going to have the same reactions, AX, AY. Well, they won't be the same magnitude, sorry. I shouldn't say they're going to be exactly the same, but if we have a pin here, then we'll have a pin. If we have the pin in the real system, we'll have the pin in the virtual system. If we have a roller in the virtual system, or the real system, we'll have a roller in the virtual system. So if you have an AX in one, you'll have an AX in the other, etc., etc. Although the magnitudes of each, and possibly the directions, will be quite different. So we have our reactions here, and in this particular one, I think, just looking at this, I'm imagining this thing bending like this, and so this is kind of interesting. Like it can be difficult to figure out which direction this thing is going to rotate. See, we have our beam here. Let's go back to the original problem. This one has a tendency. This one's going to want to deflect down like this. I think I will put a video. I think I will later put a video together just on deflected shapes. Maybe we'll go over that on Tuesday. So this beam here would have a tendency to deflect like this, and this beam here, or this column here, would have a tendency to deflect like this. And so this one would cause a tendency for the joint to rotate counterclockwise, if you think about that. I believe so. Let me think about that. That would go here, and then like that. Yeah, that would have a tendency to rotate. This load would have a tendency to cause the joint B to rotate counterclockwise, while this one would want to tend to cause it to rotate clockwise. So it's kind of interesting that these two different loads are putting opposite tendencies on the joint to rotate. So it's really not easy to figure out just by looking at it which direction this thing's going to rotate. So I'm just going to take a wild shot in the dark and say, well, this load's bigger, so maybe this one's going to take over. So I'm just going to go ahead and assume it's rotating clockwise. And you know what? There's nothing wrong with assuming something wrong. It doesn't mean that you're going to, if I get the wrong direction, it doesn't mean that I'm going to have to go back and do everything all over again. All it means is that I assumed wrong, and that's the right magnitude of the displacement, but the wrong direction. So I'm going to go ahead and assume this is 1 kip foot. Now, for those of you who have been paying attention, you may realize something is a bit amiss, and that is I've been doing all of my work in kips and feet. So if I really wanted to save myself some stress, I probably should have gone and put my lengths originally in inches, but I went ahead and did everything in kip feet instead. So I'm going to have to, at the end, at the very end, thankfully, I'm going to have to convert my E and my I to compatible units, but it's okay to work through all our virtual work expressions in kip feet if we want, but then we'll just have to take care of the units on the back end instead of on the front end. So again, this here, I assume joint B, A, B, and C. Assume B rotates clockwise. And I base this purely off of, well, that's the way that's how the beams are set up. So maybe that's how the relative sizes of the beams are. The relative loads on the beams are, or the beam and the column are. So maybe it's going to rotate that way. But again, I really have no idea. So I'm going to go ahead and get my external reactions. So let's do this. And so the first thing, I'll get my external reactions. 1, get external reactions. Now we could actually mirror the series of steps entirely from the first Roman numeral from our analysis of the real loading, or the loads produced by the real loads. But I think in this case we're actually going to be able to get away with something a little bit simpler because the loads are just so simple on this particular thing. So I'm going to first get my external reactions. I'm going to say sum of forces in the x direction. Well, the only is equal to 0, and we have AX here, and that's it. So AX is equal to 0. There are no horizontal loads on the structure, so AX is just equal to 0. Then I can do a sum of moments about point A. I don't even need to use that imagined joint D here, or point D. I can just use A here because the loads are so simple. So sum of moments about A, counterclockwise positive, is equal to 0. That's going to be equal to 20 times Cy, the moment caused by the reaction at C. 20 Cy, positive of course, counterclockwise. And then plus 1 kip per foot. That is the couple on joint B. Sorry, not 1 kip per foot, 1 kip foot. 1 kip foot. Here, 1 kip foot. And let's see here. Actually, yes, I'm actually missing a negative here. That should be minus. So that should be minus 1 kip per foot. That is in the negative direction. All that equals 0. And Cy then will equal 1/20th of a kip foot. Or sorry, actually of a kip. 1/20th kip. Then I can do a sum of moments about joint C is equal to 0. And I will get 20 times AY. And then minus the 1 kip per foot, or I keep saying 1 kip per foot, it's 1 kip foot. The 1 kip foot couple on joint B is equal to 0, and AY is also equal to, although let me think about this. This doesn't seem quite right. Yeah, these cannot be going in the same direction. So AY is equal to here. Oh, actually, that's the problem. See, in my drawing in my notes, I had this drawn in a more realistic direction. So sorry about this. I had this pointing this way in my notes because I looked at it originally and said this thing must be going in that direction based off of just estimates of moments. So if I go back to that, here, AX, if I saw moments about joint C, AY will be generating a positive moment and the one kip foot will generate a negative moment. And so AY will equal 1/20th of a kip, which will be downward because I already have my arrow downward. So this is 1/20th of a kip, this is 1/20th of a kip upward, and this is 1/20th of a kip downward. So we do have our reactions taken care of. So then I'm going to analyze the beam and the column looking for the internal moments as a function of x. Now, I'm going to be a bit lazy here, and then I'm going to try to avoid drawing the full exploded diagram because I don't want to draw a separate free... if I handled a couple on the joint, you'd actually have to draw a free body diagram of just the joints, look at the internal moments there. But I think I'm going to be able to get away with that, or get away with not doing that, just by doing some clever cutting and looking at different pieces creatively. So what I'm going to do is I'm going to get m as a function of x first by cutting this here, and then by cutting this here. I'm actually going to isolate this piece of the beam and this piece of the column. I'm going to analyze this part of the beam and this part of the column. Then I don't have to worry about drawing the free body diagram of the whole exploded view. This one's going to be fairly straightforward because we just have from the x from the end. This one will be a little bit more complex because we have x from this end, so that'll take a little bit of doing. But let's do that. So 2, let's analyze column. Analyze column AB. So we're cutting this at x, and we have this thing's going to be distance x, or length x, or coordinate x. And we have some internal m of x and some internal shear of x, v of x here. And then we have ax, or ax, which is equal to 0, and ay downward, which is 1/20th of a kip. Ay is equal to 1/20th of a kip. Now, this one's actually going to be a very, very simple moment function. If I take the sum of moments about point x, counterclockwise positive, I will find that the only moment there is m as a function of x. Ax is equal to 0, and ay and vx, their line of action passes through point x. So this is equal to 0, and mx is equal to 0. Or another way I could say this is the virtual moment in column AB is equal to 0. While there is going to be real moment, there is not virtual moment in this column. So then, 3, let's look at BC. Analyze beam BC. Actually, I'm probably going to do this on the next slide. 3, analyze beam BC. So let's consider this. I'm going to cut again at x distance from the left. Distance x from the left, that's not going to change. Again, I'm still keeping my origin constant. I need to use the same origin and direction that I did for my real moment, or the moment from the real load. So this whole thing is still length 20. And I'm cutting this at just distance x, and then, but I'm going to isolate this piece because that's going to be a little bit easier to work with, and the length of that piece is x minus 20. The length of that piece is x minus 20, so I'm going to draw a free body diagram of just that piece. So I'm going to isolate the right-hand side here. And so I'm going to assume positive shear and moment, and I'm going to point the arrows in the direction that are associated with positive shear and moment on the left-hand side of a beam. So I have v as a function of x here, and m as a function of x here, Even though this is even though this is clockwise, this is of course our positive moment convention. Then we have 1/20th of a kip here. 1/20th of a kip here. And this thing has length, not x and not 20, but x minus 20. X minus 20 feet. So then if I did a sum of moments about point x, this is going to be a really fun one. Sum of moments about point x, counterclockwise positive. I'm going to have negative m of x, because it is going in the clockwise direction, plus 1/20th of a kip times x minus 20. Times x minus 20. And so solving for m of x, I get m of x is equal to 1/20th x, 1/20th x minus 1. Or if I wanted to use that fancy subscripts, MVBC, the virtual moment in element BC, remember BC, is going to be equal to 1/20th of x minus 1. And that is our final moment expression. So we now have solved for all of the moment expressions, both real and virtual, within our frame here. Next, I'm going to step 3, or the big Roman numeral 3, is going to be to apply or to resolve integration boundaries, just like we did for beams and columns, or for beams and, well, especially beams. You don't usually have integration boundaries to resolve on your trusses, of course. So we're going to resolve integration boundaries. Now, for this particular example, this is not going to be a problem. See, going back here to our original thing, to our original diagram, original system, we have the same, each, for both the beam and for both the column and the beam, we have only a single zone of integration. So I tried to make this problem was going to be complex enough, so I decided to give each bolt but a single zone of integration. So often, though, you'll have to divide them up into a series of points, or a series of piecewise functions, or a piecewise function with a series of zones, just like we did previously when we looked at beams. So you may have to do that at another point, at another time, on a more complex example. But let's go ahead and resolve our integration boundaries. That's a really bad O. Let's go ahead and resolve our integration boundaries. But again, in this problem, I'll just note, in this problem, only a single zone of integration exists on the beam and column. Now, I suppose you can consider a zone that to be 2 zones, but usually I'm talking about dividing an individual beam up and an individual column up on each element, on each member. Therefore, no zones to resolve. And if you're having trouble remembering how to do that, please see my previous video, or I suppose that would be lecture 19, on finding on some examples of applying virtual work to beams. So, but I will just go ahead and summarize here instead. So we have column AB and beam BC. I'll just go ahead and summarize the virtual and real loads here. So we have, for column AB, or not the real loads, the real and virtual moment. The real moment is going to be, for column AB, 15x minus x squared over 2. And the virtual moment, m virtual as a function of x, is just going to be 0. On column BC, the real moment is going to be 112.5 plus 14.375 minus x squared, and the virtual moment as a function of x is going to be 1/20th x minus 1. 1/20th x minus 1. Then, so we now have our full real and virtual moment expressions for both our column and our beam. So we have completely resolved the moment for both elements, both of our members. And the final step, 4, will be to apply virtual work. So let us apply virtual work. And the principle of virtual work is, again, virtual external work equals virtual internal work. And for frames, and this can be expressed as, for rotation anyway, 1 times theta is equal to the summation of the integral of m of x, mv of x, the virtual moment expression and the real moment expression, divided by EI dx. Divided by EI dx. Now, because we have a constant cross-section and a constant cross-section, a constant moment of inertia, and constant material throughout, I can just pull this out of our expression here. And especially because this is why I designed this with the same cross-section or moment of inertia between the column and the beam, I can actually completely pull this out of the summation even. So I'm going to have 1 times theta is equal to 1 over EI. And I'm going to set up the integral for both column AB and beam BC. So I'm going to set this up and show, okay, the integral, I'm going to put this AB here, and I'd be integrating from 0 to 15, and all I need then in the inside of the integrals are my expressions, my moment expressions. So I would have 15x minus x squared over 2. That is the real moment expression, and then the virtual moment expression is 0 dx. But look at this. Anything times 0 is 0, so that goes away completely. We actually don't need to worry about the work on the column at all. So then, if I consider this here, then I'm going to consider the beam plus the integral from 0 to 20, and this would be the integral on column BC, so I can put a little BC there if I like. And then let's just substitute in the appropriate expression, times, let's see, for the real moment expression, 112.5 plus 14.375 x minus x squared, and then times 1/20th, 1 over 20, times x minus 1 dx. And we now have the full moment expression. And if you expand that out, 1 times theta here, this will still be 1 over EI, and the full expression in there will become integral from 0 to 20. If we expand out the polynomial there, let's see, we'll have, if we expand that polynomial out, we'll have negative 0.05 x to the third plus 1.71875 x squared minus 8.75x minus 112.5 dx. And if you run through that whole integral, evaluate, etc., you will get basically a 1 times theta. Everything in that integral, 1 over EI, we still have that. Everything that integral collapses to negative 1,416.67. 0.67. And this would be in units of kips and feet. So I didn't carry the units all the way through for simplicity's sake, but this would be in units of kip and feet. So now what I need to do is I finally need to resolve my unit conundrum. I didn't do this in inches, and so I need to convert my E and my I. E is 29,000 KSI. Kips per square inch, I need to convert this to kips per square foot. So I'm going to say 12 inches over 1 foot quantity squared. And I get that this has a modulus elasticity of 4.176 times 10 to the 6 KSF, kips per square foot. And I, our moment of inertia, is going to be 4,000 inches to the 4th power. That was the provided moment of inertia of the beam in the column, times 1 foot, to convert this to feet, 1 foot over 12 inches, and take that conversion to the 4th power. And I get a greatly reduced number of, although equivalent, of course, 0.193 feet to the fourth power. Then 1 times theta is equal to 1 over 4.176 times 10 to the 6 times 10 to the 6th times 0.193 times everything that was in the integral of negative 1416.67. And doing this and putting this in a calculator, I get that theta is equal to negative 0.00000176, or that is equal to negative 0.00176 radians. 0.00176 radians. And that is our final answer. So, that is a lot of work to find a piddly rotation on a single joint. I realize that is a lot of work, but it is a method that we'll be applying later on when we look at things like the force method and that kind of thing. So, I know this is a lot, and let's review through the basic steps. The first thing is to apply statics, find the member end forces, or I should say find the external reactions. We'll first analyze it for both. We have to analyze this for both the real and the virtual loads. The real loads are the real system is the geometry and support with the real loads applied. The virtual system is the real geometry and supports, but with a unit load or a couple in the case if you want rotation applied to the point of interest. So but for either the real or the virtual, you first find the external forces, then you find the member end forces. You develop moment functions for both the real and the virtual systems. Then you resolve any boundaries that exist. There weren't any boundaries here, or there weren't any boundary clashes here, so we were fine. Then you apply the system of virtual work. You work through the integral. You collapse everything down. You make sure to take care of your units. And at the end, you get your final rotation. Or if you were doing this as a displacement, you would get a final displacement in inches, feet, meters, light years if you really wanted to have fun with high, crazy, low powers of 10. But I don't recommend doing all your units. That would be a fun problem. I should do that sometime. Do a beam problem and nothing but light years and moment of inertia and light years to the fourth power. Okay, I'm digressing. Gotta get off my crazy horse. So, all right. Well, that'll do it for today. Feel free to contact me if you have any questions. Feel free to see me in class for my students this semester. Feel free to contact me in class. If you have any questions, see me during office hours, etc., etc. I hope you enjoyed this video. I hope you found it a little bit illuminating. That will do it for today. And as always, thank you.